Now, what your question, Kinga? Let's go back to what is a PWM. Okay, so back to here. A pulse width modulation signal, PWM, is a first off, just think of it as a square wave. Okay, and so just when you first start thinking of a PWM signal, think of a 50% square wave. Okay? And Kinga, if you're in your car, right, and you take your foot and you throttle for a half a second and then let off for a half a second, throttle for a half a second, let off, and you just keep on doing that, right? Let's say if you kept the throttle, whatever, down, you'd be going 60 miles an hour, right? What would you guess your car would go at if you did that pulse width modulation? 50%, you had it throttled for 60 miles an hour, 50% of the time, you're not throttled. Would you go faster, slower, what? Slower, right? Because you would be going 60 miles, well, a command to tell you to go 60 miles an hour, and then you let off and you'd be decreasing some. And then you increase, and then you decrease, right? So you would level off at some percentage of the speed you were going, okay? Now, there's all sorts of time constants in there to figure out what that 50% duty cycle would do to speed. Right? There's dynamics of your car and all this kind of stuff. Well, with a little DC motor, we're actually going to tell the motor half the time to go positive, half the time to go negative. Right? And if you do that, if you tell the motor to go positive direction, then negative direction 50% of the time, it's like the motor's not even moving. Right? Because you're telling it to go positive, then you're going no. And if you do that really fast, it's almost like you're just giving 0 volts to the motor. Okay? So that's this idea of PWM, is that we're going to, if we tell a motor or something to go positive 50% of the time and negative 50% of the time, it's almost like the motor's seeing an analog, just 0 volts. Even though really that motor is seeing, let's say it's 24 volts. It's seeing positive 24 volts, then it's seeing negative 24 volts. But because of the time constant of the motor, it's as if we're seeing 0 to that motor. Because we can PWM, the carrier frequency, the frequency which we're turning on, turning off, is so fast that the motor doesn't have time to move because of its time constant. Okay, so that's kind of, and then of course, if we're doing that, if we just, and when I draw these signals up here, right, these PWMs, if we don't change anything, this stays like that off the board, right? So this is a 50% square wave that just keeps on going until we change something. Okay? And we can. And you're going to find by changing this register compare A, CMPA, you can change the duty cycle. Okay? You could make this 25% duty cycle. And please don't go with my messy drawings. This is consistently 25%, even though if my picture doesn't look like that, right? So this is always 25%, 75, 25% on, 75% off. Right? Okay? Even though my drawings are messy. Great. And now if we're doing that again to the motor, for 25%, we're telling it to go in the positive direction. 75% of the time, we're telling it to go in the negative direction. It's going to trend to go in the negative direction, isn't it? Because we're telling it to go in the negative direction more than we're telling it to go in the positive direction, for example. Okay? And that's how, and then of course, now, if you had a motor and you 25% of it, let's say our carrier frequency. See, the carrier frequency is from the start of the edge going high to the next start edge going high. Okay? Now, if we were taking this little DC motor, or even think about, you could do it with a drill, right? Or whatever, I don't know, whatever you think of. But let's say our carrier frequency was every 5 seconds. That wouldn't make sense at all, right? So 25% of that 5 seconds, we'd be telling the motor to go in the positive direction. Well, in that because of the time constant motor, the motor would get up to speed, wouldn't it? Be going at some fast speed. And then 75% of the time telling it to go in the other direction, it's going to go back to that negative direction, isn't it? And that's a terrible control. That's awful. It's spinning really fast and then spinning negative really fast. The idea is you have to get this carrier frequency fast enough that that the time constant of the motor or whatever you're driving filters out that idea or the step response. So it just sees it as a constant value. Okay, so it's like taking this signal through you would have to play with this. We could put it in Simulink if you wanted to, or something like that. But what if we had just a very simple low pass filter? A resistor and a capacitor to ground. And this is our input from ground to input, and this is our output right here to ground. If we looked at that output, depending on the time constant of that RC filter, you should just see a constant voltage if it's the right value, right? You could do that. That's just a simple, transfer function of A over S plus A, and you could play with this A right there and bring it in a step response, bring in a square wave, and see that it comes out DC if you pick the right things. So in other words, the carrier frequency that you choose is dependent on the system you're driving. We're going to find with our motors what works really nice is 20 kilohertz. Okay? When we're dimming and brightening the LED, it's our eyeball that's the time constant. If we had a high-speed camera, you could probably see the LED going on for a little bit of time and off for a little bit of time. But your eye can't see that. That's the time constant there. So we're going to do it, I think in the homework I asked you to do it at 5 kilohertz. Okay? And that, your eye can't see that LED being off for that, 0.2 milliseconds or whatever, or however much it's off. Right? Or on, right? So you're the filter, your eyeballs are. Okay. Now, Kinga, you asked about why do we have to set registers? Well, there's one thing in this timer, in the PWM. The PWM, as I said, had a thing called EPWM 12 regs dot TB control dot bit dot clock divide. Whatever, probably got the wrong caps there. Initially, we're going to set that to 1. Well, let's think about that. All right, so now, and then remember there's a TB period, timer base period is what that stands for. And let's say for just this example, we're going to set it 1, 2, 3, 4. Okay? And we have a thing called TB compare A. Yes, oops, sorry. Compare A dot bit dot compare A. Oh, come on, Dan. Eraser, draw. Let's erase that, get it nice and neat. All right. Draw. Compare A dot bit dot. I forgot the A. Gosh darn it. Compare A equals. And for a second, let's just set that to 200 for just a second. Okay? All right. So those are some settings. There's a few more you have to do, but that's some settings. Now, what's happening here? So inside this little thing, you could, whenever you think of a peripheral, just think of a little square inside that little chip. Have you guys ever seen a picture of a processor? Right? They take it off and you got all these little shiny different areas in the chip and all that. If it's a big chunk, it's probably the RAM or something like that, right? So kind of, I don't know if that helps or not, but it's a little area on the chip. It's something this chip needs to talk to, right? On power up, it doesn't know what to do. Okay? You have to communicate with this device through a program to tell it what to do. And so that's why you have to write too. So that's part of it, right? You've got to tell it to wake up. You've got to tell it to do something. For example, if you're not using a peripheral, you shouldn't clock that peripheral because it wastes power, doesn't it? So one of the first things this processor does is turn on the peripherals it needs. And that's also in your source code. Okay? Anyway, all right. So we've got these different things. Now, first, just pictorially, what we have is everywhere throughout this processor is the 200 megahertz clock. That's what this processor is clocked at. Okay? All right. Then it takes that 200 megahertz and it makes what's called a I know it's confusing, makes a high-speed clock and a low-speed clock. These PWMs happen to be clocked with the high-speed clock. And long story, but what ends up happening is, I don't think I want to get into all the details of that because that's just confusing. All the details, but we have a 50 megahertz clock. So 50 million hertz coming into EPWM 12. Okay, that's all you need to know. And I will be telling you that. You're not going to, whenever you have to do any of these, figuring out what frequency things run at, all this, I will give you the input clock. So always look for that. Because it does get confusing in this chip to find what those all are. But anyway, so we've got 50 megahertz. And that is a square wave. Okay? And so we know the period of that square wave is 1 over 50 million, isn't it? Okay? Now, we have this little guy right here, the clock divide. That is a little part of PWM 12. And so this clock of 50 megahertz is coming into this little divide circuit. Okay? That if it's a divide by 1, the output is 50 megahertz. If it's a divide by 2, the output's 25 megahertz. You see what I'm doing? Divide by 4, etc. Right? Okay. So right now we have a divide by 1. So what's coming out of this is our 50 megahertz. Now, just as with the timer that we talked about, the CPU timers, this clock is going into the register TB counter. We didn't talk about it, but this guy. Its life, all it does, once you've set it up, is to count up to the TB period value. When it gets to the period value, it goes back to 0 and starts again. That's all it does, right? Okay? So that's why, well, it's just a counter. And then this period, that's the periodic or carrier frequency of the PRD. This is the period that this is happening, right? So what did I do up here? I put this just to some random number, 1, 2, 3, 4. Okay? So what happens? TB counter is 0. Then 1 over 50 million seconds later, boom, it goes to 1. The next 1 over 50 million, 2, 3. See what it's doing? When it gets to 1, 2, 3, 4, it goes to 0 and does it again. Never stops unless you halt it. There's a way to freeze the count. There's a register that allows you to freeze the count if you want to. But we've told it to go, and it's just going to do that for life until you change something, right? Okay, now what we do with what the data sheet draws then are timing diagrams like this. If this is our value of, well, this is really units. Every unit here is 1 over 50 million. In a sense, this guy in time, or however you want to make, you could just also do it at time. This guy counts up, 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 up. This is the counter value until it reaches TB period. I keep on putting an R there. Period, okay? And then it resets to 0 and does it again. Okay? Now, we're not going to do this with the PWM, but technically you could get an interrupt whenever TB counter equals the period. And what could you do in that interrupt? You could turn on LED if you wanted. When you came into the interrupt another time, you could turn off an LED. Agreed? Okay? And in a sense, what are you doing there? You're creating a square wave, aren't you? Because 50% of the time you turn it on, the next time in there you turn it off. So you could technically create a PWM signal in software. right? You could, if we wanted to do a 25% duty cycle, we could turn the LED on the first time we come into that interrupt, and then the next 3 times, make a count, the next 3 times keep it off. And then when that 4th time, we turn it on again, and then 3 times off. That would make a 25% duty cycle, wouldn't it? But that's taking a lot of processor checking those counts or whatever to create the duty cycles and all this great stuff. That's taking a lot of processing time. Why don't we let a hardware device do that for us and turn on a GPIO at a certain time and turn it off at a certain time? And in that way, we can create this PWM signal. Okay. Now, we're almost there. So, Kinga, to your point, what if I wanted to make a slow PWM signal? Or slower, at least. I could change this divide, couldn't I? If I change the divide, then the amount of time it takes to count up to 1, 2, 3, 4 would be, say if I did divide by 2, it would take twice as long, wouldn't it? Or if I set it to 3, it's a divide by 4. It would take 4 times as long, or whatever, right? So do you see, that's why you need to write to a register to make those changes. That kind of answer? Okay, good. Now, we'll talk about probably more of this in lab. Well, we can talk about it Monday too. We'll keep on this. But now there's these 2 events that happen. What we do also, there's this register, the top half of compare A. That top half is 16 bits also. We set that to 200. Well, with this other register called the action controller, AQCTL, you can tell an IO pin what to do when the counter reaches both of one of these events. Okay? So let's think about this. So what's going to happen here? This is where 200 is on this register. This is 1, 2, 3, 4, the period value. 200's right here. 1, 2, 3, 4 is right here. And it keeps on repeating, doesn't it? This is 200. That's 1, 2, 3, 4. We can, with the period, we can say whenever the counter equals compare A, I want to set the IO pin associated with PWM 12, I want to set it low. Okay, let's think about what that does. Draw, erase. You have to talk every time I talk that through. It's kind of funny. All right, so let's say what we want to do is when we see this, we want to pull the IO pin low. Now, we can also, there's an event when it equals the period, and there's also an event when the counter equals 0. I don't know if that's 1/50 millionth difference from each other. I don't think there's much difference. So anyway, I usually use the 0. And what we're asking you to do in this exercise is to, whenever the counter equals 0, in other words, when it's reset to 0, we want to pull our IO pin high. So think about what that would do. Our IO pin, well, it's 0 here, so boom, it gets pulled high. And then when TB counter equals 200, it goes low. And then it stays low until the period equals, till the counter equals 0 again. High. Gets to 200, goes low. High. Low. See what I'm doing? So, you did not have to pull that IO pin out. You're not going to do any GPIO regs clear or GPIO regs set and all that, remember? This is all done for you inside the CPU, inside the PWM peripheral. Okay? And look, what if we change now, compare A to 500? Or better, let's say 617. What would be our duty cycle? Whatever half that is. 50%, right? What if we change that, if we change the value of compare A to 75% of 1234? It'd be a 75% duty cycle. Would you ever want to make compare A bigger than the TB period? If you did, it would just always be high. So anything greater than that would just still be 100% duty cycle. So your compare A value is a percentage of, it's an integer, so it's not exact percentage, right? It's rounded, it's truncated, but your compare A is a percentage of period, and by changing to that, you change the duty cycle of your square wave. And finally, the value of TB period determines your repeat rate, or what we call our carrier frequency. Right? I say one more thing. Sorry. And that amount of time is what? That amount of time is 1234 times 1 over 50 million. That's the period of that. Does that make sense? Because each count is 1 over 50 million. So 1224 times 1 over 50 million, that's the period. Inverse of that is your carrier frequency. All right, so think about that. Good, excellent.